Thank you very much. I was asked to make clear the way that the isomorphism between RD and TD, the Hecke algebra, TD, and the universal deformation ring makes E modular. So we started with some rho bar that was the mod P representation, and suppose that the full p-adic representation, rho EP, is indeed a deformation of that minimal type that I'm discussing, D, which I told you yesterday when it is. Then there will be, of course, a homomorphism from R to O, or actually to ZP in this case, just specializing the universal deformation to that particular one. And if you know that R is T, then you can complete this diagram. And this means that you have a map from T to O, making this commutative. But of course, the universal representation here, the universal deformation here, is such that the trace of this on a generic Frobenius of L gets mapped here to TL. So this means that this TL, the Hecke operator TL here, will be mapped here to the trace of rho EP on Frobenius of L. Now, the only remark that I have to make is that a homomorphism of T to O is essentially an eigenform. And this is a remark I think that Ken made, and this comes from the fact that such a homomorphism, for example, you can view it now in characteristic 0, so you may just as well tensor T with Q, and then it breaks into, at least in the reduced case, but we're interested only in almost all else, it breaks as a product of fields corresponding to the different eigenforms. And from that fact, you get the basic idea behind everything where we use the Hecke algebras, and this is that a homomorphism from the Hecke algebra to O is like giving an O-valued modular form, eigenform for the Hecke operators. So this shows that what we capture by saying that R is isomorphic to T is really that the representations are the same, that the representation is modular, or the L series, if you want, is modular. Now, people all know, but I think it hasn't been said here, that there's still one step from this to the geometric fact that, in fact, the elliptic curve has a modular uniformization. But this uses the, well, Falting's isogeny theorem, but in this case, where the J invariant is non-integral, and then we're talking about elliptic curves, it's due to Sayre. However, for many purposes, you don't need this geometric fact. For example, if you're just interested in the analytic continuation and functional equation of the Hasse-Weil zeta function, it's enough to know that this Hasse-Weil zeta function is the Hasse-Weil zeta function of a cusp form of an eigenform. So I hope that these remarks clarified some of the questions that I understand were raised yesterday in the problem session. Okay. So we are going now to finish the proof of what we started yesterday, and I'll remind you that I used the criterion that I called the Wiles-Faltings criterion, but probably should be better called the Taylor-Wiles-Faltings criterion, for R to be isomorphic to T. And I will not write down all the requirements, but basically there were requirements about the TQs that we introduced, with which we dealt yesterday, and now we're going to deal with the RQs. And the only thing that we really have to make sure is that we can choose our set of Qs in such a way that these RQs, although they grow vertically, so to speak, deeper and deeper, and not horizontally, in the sense that they can all be uniformly generated by the same number of elements generators R. And in fact, I will prove the following proposition. So I'll call it proposition 2. There exists a number R, which depends only on the representation rho bar in question, such that for all n greater than or equal to 1, there exists a set Q of R primes with the following requirements. First of all, it's disjoint from sigma. For all Q in Q, Q is 1 mod p to the n. For all Q in Q, a rho bar of Frobenius at Q has distinct eigenvalues alpha Q and beta Q. And finally, and most important, RQ is topologically generated by R elements. The same R, that's very important. Not just that they are uniformly bounded to the number of generators, but it's the same R as the number of primes. So with this, we have all the ingredients that go into the Taylor-Wiles-Faltings criterion, and that's our task to do this today. Now, I'll remind you that the minimal number of generators for RQ is the dimension of MRQ over MRQ squared, maybe put lambda here, over K. So that's as an O algebra here, as topological O algebra. And this dimension is also equal, of course, to the dimension of H1 dq Q in the adjoint representation, because these are dual vector spaces, and this was discussed by Maser. So I think that it's clear now that really, let's call this number R of Q perhaps, R of Q, the minimal number of generators of this topological complete local Noetherian ring. It's clear that we're really interested in knowing something about this dimension. And for that, we will recall things that Larry Washington did. Let me push down this one and up. This one and send this one up. Oops. Okay. So let us put W to be this module, the module for the trace zero, or traceless as people put it, matrices under the adjoint representation of rho bar. The dual one, Hom W mu P, is isomorphic to the Tate twist of W, because of course W is self-dual if you do Pontryagin duality. So here the mu P. And this is also, by the way, the symmetric square of rho bar. Now also, if rho bar is Selmer, then there is a filtration that defines the Selmer condition, and you will define W0, that's exactly the W0 that figured in Washington's talk, to be the homomorphisms from U over U naught to U naught. In other words, it's those things, right? The things that map U to U naught and kill U naught. And W1, we will need this perhaps, the homomorphisms that simply preserve the filtration of the pair U naught, but those, of course, of trace 0. So there's filtration W naught inside W1 inside W, where the quotients are one-dimensional in the Selmer case. And let's recall the local conditions that were defined in Washington stock. LP is H1 flat GPW in flat case, where the flat classes are those that represent extensions, infinitesimal extensions, that are themselves flat as representations. And it's H1 Selmer GPW, which is the kernel of H1 GPW to H1 IP W over W naught in the Selmer case. Then for L not equal to P, LL is H1, the unramified ones. I knew that it would come. Okay, sorry. H1 GL over IL W IL. So these are simply the unramified classes sitting inside H1 GL via inflation. And finally, L, so that's for L not equal to P, but L dividing the conductor of rho bar. And finally, for the Q's that we introduced, there is no condition. LQ can be anything H1 GQW. Well, the determinant condition is built in because I'm only taking the trace 0. They're not traceless because 0 is a number, but the trace 0 things. Now, we will use L star to denote the dual under Tate duality. And it was already remarked that L star L for L different from P is similar in the sense that it's the same thing basically, but with W star instead. It's also true in the flat case. I want to make a little remark here that, of course, if you define the flat things using extensions, then there is no interpretation of W star using extensions. Okay, W you can understand using extensions, not W star. But there is another interpretation of the flat ones a la Bloch-Kato using Bloch's Fontaine's construction of the ring B-crease. And with that, you can define H1F of W star, and then H1F of W becomes just the exact annihilator of H1F of W star. What I'm trying to emphasize is that away from Q's, somehow the minimality is reflected in the fact that the lattices that you choose to define the local conditions, to define the Selmer group, the L's, just sit right in the middle somehow, in the sense that their exact annihilator is of the same shape, but rather with W star. For LQ, of course, that's not true. LQ star is 0. And we define the Selmer group H1D Q W star, W first, to be the kernel of H1 G sigma, well, we don't allow ramification outside sigma. Sigma is the set of ramified primes. W to the product over all L's in sigma LL. This includes P. P is in sigma. And similarly with a Q, if I put a Q here, here you would have sigma union Q, and here you would have sigma union Q. Okay, the same thing. So if you put a Q here, you enlarge this Selmer group in the sense that you relax the unramified condition at Q, that's all. And H1 D star Q W star to be similarly the kernel of H1 G sigma W star to the product of the LL stars. And the importance of the Selmer group comes from the fact that I mentioned already that H1D QW is isomorphic to the homomorphisms from MR over MR squared in lambda into K. So in particular, its dimension is this number that we denoted by R, well, RQ if you put here a Q, which is the minimal number of generators. That's the number we're after. I say if that's without a Q, then it's G sigma. If it's with a Q, it's G sigma union Q. If I put a Q here, then put sigma union Q here. Okay? And then you relax the condition. No, it's LL. In my notation, it's LL. Okay, you want, oh, sorry, you're absolutely right. It's H1 over LL. Thank you. It's, if I wrote the kernel, it's H1 over LL. Thank you. You're absolutely right. And here the same thing. I apologize. I want the things that land inside LL, not obviously. There is no map from H1 to LL, right? Okay, and the computation that I'm not going to do because it's very simple, is that actually the conditions as we put them translate into the right LLs. Okay, so for example, the flat case, it was just the definition of H1 flat. But let me just indicate how you do it. For example, in the P-Selmer case. In the P-Selmer case, remember that the cocycle that was constructed from a deformation was C rho of G given by rho, from an infinitesimal deformation given by rho G rho bar G inverse. So if you, right, and this is in 1 plus epsilon W. So it's W because we fixed the determinant. And for example, if you restrict now G to the decomposition group at P, then from the condition of being a Selmer deformation, it's easy to see that this lands, in fact, in epsilon W naught. So modulo W naught, you go to 0, at least on inertia. And if you landed in such a space that goes to 0 in inertia, then at least restricted to inertia, it will be of the right triangular shape. But then since inertia is normal in the decomposition group and it has a unique fixed line, that fixed line will be also invariant under the full decomposition group. So you will get your triangular shape over the whole decomposition group. So in fact, these are the right conditions to put. And the problem is that we cannot directly say what the size of this group is, but thanks to the long exact sequence of Tate and Poitou, the 9-term exact sequence, and the identities derived by Greenberg and Wiles from that, you can say something about the ratio of these two. So I will write it down now. So you have that H1, I'm writing simply the cohomology groups, but I mean their order. I don't want to write this sharp always. H1D QW divided by the order of the dual Selmer group is equal to H0, dual Selmer group is equal to H0 QW divided by H0 Q dual times the product over all the places in sigma and infinity of this LV that was defined up there over H0 GVW. And if you put a Q here, you simply had to put a Q here too. So let's compute the local terms. In this important sequence, in this important equality, in fact. So first we start with LP. I claim that the number of elements in LP divided by the number of elements in H0 GPW is simply, it's one dimensional over the field, okay? It's just computing dimensions if you want. Now in the flat case, this was done by Conrad. That was his main theorem. And in the Selmer case, this was almost done by Washington. If you remember what Washington called the horrible computation in Galois cohomology, except that, in fact, in our case, because we assume that it is Selmer non-flat, the computation is a little bit easier. So if you follow Washington's notes or the computation that he asked you not to copy from the blackboard, if you did copy it, then you will see that somewhere he has an inequality there, and thanks to the fact that this is Selmer, that inequality is an equality, and you know this result. At infinity, we have that the number of elements in L infinity divided by the number of elements in H0 G infinity W. That's very easy to compute. That's 1 over number of elements in the field. And in L, dividing the conductor of rho bar, then I think also Washington mentioned that this is one. I don't know if he mentioned the reason for this. I'll mention it quickly. You have an easy exact sequence, H0 GL W, the invariance under decomposition. Go to invariance under inertia. Go to invariance under inertia again under phi minus 1, phi is Frobenius. Go to H1 GL over IL with W fixed by IL, and that's surjective. So you see by computing all things are finite that the order of this over the order of this is sorry, that the order of this over the order of this is the order of this over the order of that, and these are the same group, so these two have the same order. So we have all the local components under control, and fortunately it's kind of a miracle that the p component and the infinity component just cancel each other. The rest give you 1. I haven't touched the q yet. I'm still doing the empty q. How about h0? This is 1 simply because w is irreducible. And this is 1 because w star is irreducible. And for the irreducibility of w star, we use the assumption that rho bar restricted to GL is irreducible. So rho bar restricted to GL, remember L was this field Q root minus 1 to the P minus 1 over 2 times P, is absolutely irreducible, implies that that W star is irreducible. We will use this again. That's a little exercise. So these are 1. So you see that in the case where Q is empty, this is 1. And that's a very interesting feature, that the Selmer group and the dual Selmer group have the same cardinality. Now what happens when Q is not empty? H0 GQ, now I'm taking the Q's that are in my Q, W is K. And why is this? You see, the W, remember that rho bar was in fact diagonal, right, with eigenvalues alpha and beta, which were distinct. And on W, the eigenvalues are alpha over beta 1 and beta over alpha. So there's, of course, one space of invariance. The same kind of computation shows, or the same argument shows, that H1 IQ W, well, these are just homomorphisms. W is unramified at Q. Invariant on the GQ over IQ is K. Okay, why? Because these are homomorphisms, of course, from the tame inertia to a 3-dimensional space, but that are invariant under the unramified quotient. Now, the unramified quotient acts on this via the cyclotomic character on tame inertia. But the cyclotomic character, since Q is 1 mod P, is trivial. So it's the same as asking for the homomorphisms from IQ, from tame inertia here, to the fixed part of W. So that's, again, homomorphism from, there's a ZP in the tame inertia to K, that's K. And the H1 of FQ W is W over phi minus 1 W, which again, for the same reason, is K. So you see that via inflation restriction sequence, from here you get that H1 GQ W is K squared, and divided by H0. This was the LQ, right? Divided by H0, you get a 1-dimensional space. So HQ, do I still have, luckily I still have the important sequence there. Each Q gives you one more dimension on the right-hand side. And now I can state the important corollary. A, this RQ, which is the dimension of the Selmer group, with Q, how did I write it? Is equal to the dimension of the dual Selmer group with Q plus the cardinality of Q. And the second thing is that when we add a new Q to Q, either H1 dq, I'll write it for short, I will not copy, either H1 dq goes up by 1, or, and that's exclusive, or H1 d star q drops by 1. So when I saw this, it reminded me, but that's just, it has no meaning. It's just the kind of situation that you face when you study Riemann-Roch. That you have such a formula, an exact formula, and you play with your divisors, and each time you increase the degree of the divisor, either one side goes up by 1 or the other one goes down by 1, and you want to choose the divisor, say if you're studying Weierstrass points or something in a clever way, and that's exactly the kind of argument that we're doing. I'm not pointing to any analogy. But why? So A, I explained why is B true. B is true because you see suppose you add a new Q, then what have you done? You have relaxed the condition at Q, which previously was unramified, to nothing. So to capture the old condition of being unramified, you have to use the linear functional into this space, which is one-dimensional. So that's why either that goes up by 1 or the other one drops by 1. Okay, so now we have the proposition that we want to prove. No, down, up. So the proposition is, let R be the dimension of the dual Selmer group without the Q's, and this is going to be the mysterious R that figured everywhere yesterday. People asked me, what is this R going to be? Here it is. It's also the dimension of, that's also what I denoted by R empty. It's also the dimension of R, of the Selmer group. And for every n, there exists Q of R primes, this number of primes, congruent to 1 mod p to the n. As above I mean not in sigma, and eigenvalues for rho bar of Frobenius at Q being distinct, such that H1 dq star q w star is 0. In other words, we can choose the Q in such a way that in each step of the two possibilities in B, this drops by 1 and the other one remains the same. Okay, of course, after it drops all the way down to 0, if you add more Q's, the H1 dq will start going up. But you can choose them in such a clever way. Now, what this mean? This would imply, of course, that the R of Q is this R. The dimension of H1 dq is R, and this is what we wanted, right? Now, this is the big miracle that makes everything tick, that somehow the same R, the number of Q's used, is the R that turns up in the dimension of this Selmer group. You see the number of Q's in Schroff's lecture, in the commutative algebra would produce the number of variables S, right, that correspond to diamond operators. The number, the dimension RQ, the dimension of the Selmer group, would correspond to the number of X's, to the number of generators. And it was you had to have a very tight equality, because the whole argument was an argument on cruel dimensions that relied on this equality. If you were not in the minimal situation, and this is how the minimality is used in a very strong way. If you were not in the minimal situation, if a priori this quotient without the Q's was not 1, if the Selmer and the dual Selmer group without the Q's were not equal, then you would be in trouble. So I want to emphasize this point. So how do we prove this? Okay, so since H1, as I said, dq star qw star is the kernel of H1 d star qw star into the product over q in q of H1 of these one-dimensional spaces that I described before, H1f qw star. Oh, by the way, I didn't say that H1f qw star and H1f qw are the same, right? Because q is 1 mod p. So, okay. So to prove, so it's enough because of this. What we want is in each step really to kill one element here. So it's enough to prove the following, that for any psi in H1 dq star qw star, there exist infinitely many in H1 d star. Okay, yeah, it's the kernel from here. We want to kill this. There exist infinitely many q's such that q is 1 mod p to the n, such that alpha q and beta q are distinct, the two eigenvalues as before, and such that the restriction to the decomposition group at q of that psi is not 0. 3 important conditions, okay? Now this is the point where Chebotarev gets into the picture and allows us to translate this to a problem on the existence of certain elements in Galois groups. So by Chebotarev, enough to show, given that psi, so now we're given this particular psi that we want to kill, enough to find sigma in the Galois group of Q with the following properties. First of all, sigma is trivial on Q zeta p to the n. That reflects the first thing. Second, rho bar sigma has distinct eigenvalues. And the third point is that psi of sigma is not contained in sigma minus 1 W star. Okay, why? Because then take Q whose frob is equal to sigma on a large enough field, on a field that contains the splitting field of rho bar, the splitting field of psi, and zeta p to the n. And then the two conditions correspond to the first one, and you see the image in H1 FQW star, H1 FQW star, if sigma is going to be the Frobenius, H1 FQW star is W star modulo this. So the image is going to be non-zero precisely where psi sigma, restricted to sigma, is not in sigma minus 1 W star. This condition comes from the fact that you want to make sure that your psi goes to something that is non-zero there, so that the condition that it does go to zero in fact kills this psi. Okay, so now I need a big diagram of fields, and we're going to do some Galois theory. I'll put the diagram of fields here. Here's Q at the very bottom. Here's Q zeta p. Here's Q zeta p to the n. Let's call this group delta, cyclic of order p minus 1. Let F be the splitting field of rho bar over Q zeta p to the n. If you want a splitting field of rho bar, join p to the n roots of unity. And K, similarly, splitting field for add not rho bar over the same thing. Let's call this group H, and this group H twiddle. And we will later need the splitting field for rho, which I will denote M, for rho bar. So M to F is a cyclic P group. And this I denote by G tilde, and in fact let's put another field N, which is similarly splitting field for add 0 rho bar, and this I will denote by, well, it's not necessarily, doesn't necessarily contain Q zeta p. Let's denote this by G. Okay, these are all the fields that I want. And you see the kernel, of course, one important thing to notice is that a matrix acts trivially in the adjoint representation, even in the adjoint representation on traceless matrices, if and only if it is a scalar. So this kernel here, for example, is just the scalars. I think I want to denote it by Z. Yeah, this is Z. So Z is just the scalars in the image of rho bar. And this can be smaller than Z, depending whether this n fixes Q zeta p or not. But it's the scalars in the image of rho bar restricted to Q zeta p to the n. Okay? Now we need a lemma whose proof I will postpone. Now let me erase this. Or maybe, no, let's leave this. If I need a diagram, I will bring back the blackboard, as complicated as it is. So let me call this lemma the group theoretical lemma, because its proof involves some group theory, unlike all the rest that we did. This is that H1 K over Q with W star is 0. Okay? So K is the splitting field for edge 0 rho bar, but so that's W, but since K is over Q zeta P, at least, then it's also the splitting field for W star. See, W and W star differ by the cyclotomic character, but as long as you restrict the representation to Q zeta P, definitely if you restrict it to Q zeta P to the N, then they have the same splitting field. They're the same representation. So we will prove the lemma at the end, but let me show how the lemma implies all that we want. Okay? So you see, psi restricted to, so psi is this cocycle or cohomology class that we want to kill. And in H1Q of W star, okay? And I restrict it now to the Galois group of Q bar over K. So this becomes a homomorphism from GK to W star, of course. But not any old homomorphism, but the one that's fixed by the Galois group of K over Q. That's via restriction. That's a restriction sequence. Now what this means, sorry, in particular, is that psi of GK is not just any old subgroup of W star, but a sub-Galois module of W star. Okay, if you want to see how Galois changes something in the image, conjugate the thing here, and then you will see what's the impact there. So is a Galois submodule of W star. Okay, so we already noticed that the condition that rho bar be irreducible when restricted to this quadratic field of conductor P means that W star is irreducible. So this is a non-trivial submodule, so psi of GK is all of W star. Sorry? Yeah, K-linear span. Yeah. If K is FP, then it's okay. K-linear span. So now it is possible to find sigma naught, and for lack of time I will not do it, in the Galois group of Q zeta P to the N. That's a good exercise, in fact, that again comes from the irreducibility, such that rho bar sigma naught has distinct eigenvalues. In other words, if you just wanted the alpha Q different from beta Q and Q congruent to 1 with P to the N, that's a consequence of the irreducibility of rho bar. And let's take this sigma naught, and on W, so if we call the distinct eigenvalues alpha and beta, on W it has eigenvalues alpha over beta 1 and beta over alpha. And we have, and that's the same on W star, because alpha times beta is 1, because it fixes zeta P, definitely. So definitely sigma 0 minus 1 W, sigma 0 minus 1 has an eigenvalue of 0, so it's not invertible. So sigma 0 minus 1 W star is not everything. And therefore, psi of GK is not contained in here. I'm a little bit worried about this point of K-linear span, but I didn't pay attention to it, but let's leave it as it is. Psi of GK, or at least the K-linear span of it, is not contained in there. And we're looking now look for sigma in the shape tau sigma naught, where tau is in GK. Okay, so first of all, definitely K contains zeta p to the n, sigma naught fixes zeta p to the n, so sigma will fix zeta p to the n. Rho bar of sigma is the same as rho bar of sigma naught, or at least, well, maybe up to a scalar, because K is not a fixed field of rho bar, but definitely changing by multiplying by a scalar doesn't change the property of having this, distinct eigenvalues. So up to a scalar, so has distinct eigenvalues. So that's the second property that we wanted. And how about the last property? Psi of sigma is psi of tau plus psi of sigma naught. Okay, in general, you'll have the cocycle condition, but tau is in GK, it acts trivially. So that would be of tau of psi of sigma naught, but that's psi of sigma naught. Now, if psi of sigma naught was not good in the first place, in other words, if psi of sigma naught happened to be in sigma naught minus 1 W star, because psi GK is not in there, you can move it out by psi of tau. You can choose tau in such a way that it moves it out. So this can be chosen not to lie in sigma naught minus 1 W star, which is the same as sigma minus 1 W star, because tau acts trivially. So this finishes the proof modulo the group theoretical lemma, and I will try now to sketch very quickly the proof of the group theoretical lemma. No, that's not good. I really need now the, sorry, I need the diagram. So I'm going to bring this up. And I'm simply going to erase this. Okay, so this is the end of the argument. I need this half of the blackboard because now all my arguments are going to be on this diagram. So I'm going to prove the group theoretical lemma. So first of all, it depends on the classification theorem of subgroups of PGL2 K, which says that any such subgroup is conjugate to a Borel over the algebraic closure, or conjugate to PGL2 K prime, or PSL2 K prime for some field K prime, finite field K prime, or D2N, the dihedral group where N is relatively prime to P, or A4, S4, or A5. So that's a classical theorem of Dixon, at least the analog over the complex numbers, but I think that Dixon proved this. Blackboard is too small or the chalk is too big. Well, I think maybe I will just take this up, and anyhow, if I need it, I'll bring it down. At least you see it. It's visible. So now we have a case-by-case argument. Remember that Z was the kernel of G tilde to G. These were the scalars in the image of rho bar. It's still written there, the Galois group of M over N. So case 1 doesn't need the classification and is the easiest. That's if Z is not plus minus 1. if z is not plus minus 1, then W star z is 0. Why? Because, you see, the scalars, of course, fix W, right? Because they're in the center. And the determinant of the scalars, if they're more than plus minus 1, is more than 1. So they act non-trivially on the p roots of unity. And therefore, they do not fix the p roots of unity. This is irreducible. Z is a normal subgroup. So this must be 0 if it's not the whole thing. OK. But in this case, remember that Z has order prime to p. So we can use, OK, so now the next thing to note is that Z has order prime to p. F over m has order, which is a p power. Z is cyclic. So we can actually think of Z as a subgroup of Galois F over K. We can lift it. We can lift the field m over n to a subfield of F. It might be strictly contained in K, OK? So let's call this field simply F fixed by Z. And H1 of F fixed by Z over Q W star Z, which of course is 0, must be H1 of F over Q W star by inflation restriction, since the order of Z is prime to p and W has p power order. And this is 0, this is 0, all the better. H1k over Q with W star is 0. This is the easiest case. The next case, I'm running short of time, is when Z is plus minus 1 and P is greater than 3. OK? Then delta is cyclic of order P minus 1. And if you use the classification theorem and you check case by case which cases can occur, which G tildes have quotients that are cyclic of order P minus 1, you're reduced into two cases. So by the classification theorem, either G is contained in a Borel, in which case G tilde is also contained in a Borel, or G has order prime to P, in which case G tilde has an order prime to P. This case is treated in a similar way using inflation restriction. And I don't have the time. It's easy. And this case contradicts the irreducibility. So let us agree that this case is done. Finally, there is the case where Z has is plus minus 1 and P is 3. Z is plus minus 1 and P is 3. And again, the classification theorem tells you, and the same kind of arguments that I used before, tell you that the only case that one has really to consider is where G is PGL2 K prime for some other field K prime. And now the argument breaks into the case where K prime is not F3 or is F3. So in the case that it is not F3, Wiles has an argument based on a paper by Klein, Parshall, and Scott, some rather heavy hammer. And I think there's a little trick that one can do here. You see, G tilde in this case, I claim that this case simply can't happen. G tilde in this case is contained in GL2K, but projects onto PGL2K prime. So first of all, it's immediate that it contains SL2K prime, right? Because take any two elements in GL2K prime, then up to scalars it contains them, so it contains the commutator of them both. Therefore, it contains the whole commutator subgroup of GL2K prime, which is SL2K prime. Now, in SL2K prime, you already have the scalars plus minus 1 that are the only scalars in G tilde. Okay? So therefore, G tilde over SL2K prime must have the index 2. Okay? Right? Because this projects to PSL2K prime, which is of index 2 in PGL2K prime. So this has an index 2. Now, that can't happen because on the one hand, since the determinant is omega, or more generally it's odd, you have to have an element of determinant minus 1. So that already exhausts G tilde together with this. But an element of determinant minus 1 is not in, will not be sufficient to cover PGL2K prime, because minus 1 is a square in K prime, because K prime is not F3. K prime is not F3, minus 1 is a square, so you need still, if it covers all PGL2K prime, you need an element whose image is, well, that's what distinguishes, right, the elements in PGL2K prime that are not in PSL2K prime. So I think that this argument is a valid one. I did it rather quickly, but you can avoid the Klein-Parshall-Scott argument. Anyhow, it's a very special case. The most interesting case is maybe what we will denote 3-2, which is when K prime is just F3. But there you do it by hand. You see, in this case, again, it's just the G tilde is a full GL2 F3. It has not G tilde, but G, I guess. G is the full PGL2 F3, so it is S4. It has a V4 in it. That's, somebody already did it, maybe Tunnel. There's a V4 in here. You can lift the V4 to there. And you can argue that V4 is normal, in fact, not only is normal all the way down to Q, and by inflation restriction sequence and the fact that the order of V4 is prime to 3, you can argue as before and finish the proof. So this is some group theory that allows you to finish the proof. And with this, we have the minimal cases. Maybe I'll take one more minute just to give a little exercise. You know, Glenn asked us to give exercises. I think what we haven't seen so far is an example, a numerical example where these things work. So just to give you an example, if you take the curve y squared plus xy equals x cubed minus x squared minus x, then compute the minimal discriminant is 73. Then rho bar E3 is full. That's actually a nice exercise. You'll have to consider the reduction mode 2, I think, of this curve. Image equal GL2 F3. It has good reduction outside 73. It's flat at 3. In other words, that's a supersingular curve mode 3. And because of the fact that this is 73 to the first power, this is a case where the minimal deformation works. So the theorem that I sketched so far, without having to go from minimal to non-minimal and without having to deal with irreducibility of rho bar, already proves that this is a modular curve. And in fact, I took it from Antwerp, of course. That's the curve 73A in the Antwerp table. So at least there's one case where we can say that the theorem works. Thank you very much.